Here is what we call as photoelectric effect. Okay, do not be afraid of all of this. I have written it. I have written it at one place. Okay, so that it becomes easy to understand, it, to explain, understand, and relate things. Okay, and that's all. The best thing is that's all. That's all we need to understand photoelectric effect and then to be able to solve problems. Okay, let's start discussing it. You don't really have to note down all of this all at once. Okay, let's do it one by one, and then you also keep on making your notes. Okay, this is a simple experiment. This is the experiment of photoelectric effect. Now, if someone asks to explain photoelectric effect in the simplest possible term, okay, it is like this. If I have a metal surface, okay, and if light falls on it, this is light, EM waves, light falls on this metal surface, then electrons are ejected. Electrons come out of the surface. This is known as photoelectric effect. Photoelectric effect. Now, as the electrons come out, I start with a neutral plate. This plate is neutral. Light falls on it. As the electrons come out, okay, this plate is going to be positively charged. Positively charged. It will start attracting back the electrons. Okay. So if I do not make any arrangement, okay, then these electrons are going to gather around it. They will not go far from this metal plate because the metal plate becomes positively charged. Electrons will be attracted back. Okay. So what will happen is they will make a cloud. That is electron cloud around this metal plate. Okay. I need to remove these electrons. Okay. I want to clear this cloud of electrons. Now, for that purpose, all of this arrangement is made. Okay. Even if I do not have all of this and light falls here, this is light falling on this metal plate. And this is known as emitter because electrons are emitted. That's why it is known as emitter. Now, what we do is we keep this plate at positive potential, and here this as negative. Okay, so what will happen is these electrons will be attracted, okay, attracted or repelled. Okay, this is a variable potential. This is variable. Okay. Now, if I want to attract those electrons, in that case, I will keep this at positive potential, and this at negative potential, such that electrons are attracted. And when the electrons are attracted, okay, electrons go from this plate to this plate. Now then they will come back here. The circuit will be complete, and I will have a current in this circuit. Current in the circuit. The purpose of this is to create a potential difference between these two plates. It is known as emitter. This is known as collector. It collects the electron. Okay. So this experiment is carried out, and certain observations are made. Okay. Let's look at those observations. All the observations. We have four observations, four important observations. First, second, third, and fourth. Okay. First observation. This whole thing is it was not expected. Okay. What is the meaning of not expected? What it says, emission of electrons is instantaneous. There is no time lag. Okay. That means the moment light falls on this, immediately we register current here. Immediately. Okay. That means the moment light falls, immediately electrons are ejected. emission of electrons is instantaneous. The moment light falls, instantaneously electrons are ejected. There is no time lag. Okay, so what's the problem? Okay, that's fine. So what's the problem? The problem is this is not an expected behavior. Okay. When this experiment was carried out, when this was observed, at that time, the wave theory of light was prevalent, or let's say that was the only theory. By that time, it was firmly established that light indeed is a wave and nothing else. It's a wave. Okay. Now, if it is a wave and it falls on this metal surface, okay, so EM wave has energy in its electric and magnetic field. That energy will be absorbed by the electrons. It is going to take some time. It is going to take some time. Okay. Also, to liberate the electrons, to take out the electrons from metal surface, from the metal, some energy is required. So we need to provide that much energy to the electron, and only then electrons will be ejected, and that is going to take some time. Even if it is a microsecond, even if it is a millisecond, whatever it is, okay, it is going to take some time. Okay, but that was not observed. That's why it is written, it was not expected. Okay, that means the wave theory of light could not explain this behavior. Okay, second, electrons are ejected only if frequency is more than a certain value or wavelength is less than a certain value. Okay, irrespective of okay, I'm adding one more thing here. Okay, I'm adding it. Irrespective of intensity. This is the observed behavior. Now, I have not written everything. Something I'm explaining. During explanation, okay, I will be explaining many things. You should note it down in your notebook. Okay. First thing, I'm doing this experiment. What I notice is that if the frequency is less than a certain value, then no matter how intense my light is, electrons are not ejected. Note down this. If the frequency is less than a certain value, or if the wavelength is more than a certain value, then electrons are not ejected no matter how intense the light is. Okay, and then on the other hand, if the frequency is more than a certain value, or if the frequency, if the wavelength is less than a certain value, then electrons are ejected, always ejected, no matter how small the intensity is, no matter how feeble is, very weak, no matter how feeble the intensity is. Are you able to understand it? Okay, note this point down in your notebook, in your own language. I'm repeating this again. No matter what the intensity is, even if it is very highly intense light, but if its frequency is less than a certain value, no, it's not going to work. Electrons are not going to be ejected. In terms of wavelength, if it is more than a certain value, not ejected, no matter how intense the light is. On the other hand, if the frequency is more than a certain value or wavelength is less than a certain value, then electrons are always going to be ejected. No matter how feeble, how weak the intensity is, how low the intensity is. Electron, even if the intensity is very, very low, but the frequency is more than a certain value, electrons are going to be ejected. This was absolutely not expected. Absolutely not expected. Okay? That means the wave theory of light could not explain it. Not at all. Okay. Now the third one, maximum kinetic energy. Okay, electrons are ejected. Electrons are ejected. It's like this. It's like this. Okay, I'm explaining it here. I'm explaining this here. Now, this is my metal surface. My metal, full of atoms, full of electrons, many electrons, large number of free electrons in metal surface. Okay, atoms also, large number of atoms here, here, full of atoms, full of electrons. It's like this. What are these? These are atoms, atoms of the metal. And then there are electrons, electrons here, electron here, electron here, electron here. One electron is here, right here. One electron is right here, okay, deep inside. Electrons and atoms. Light falls. Light falls. Okay. Let's say that light falls, and this light, the energy of this light is absorbed by some electron here. Now, this electron absorbs the energy, and its energy is more than the energy that is required to free it. Okay. Here, let me just point it to you. Minimum energy required to liberate electrons for every surface, for every metal has this characteristic value. Okay, that is known as work function. It is known as work function. Okay, suppose that I have this metal plate, this metal, any metal. Let's say that its work function is 2 electron volt. 2 electron volt. It is the work function of this metal. Then what it means is, I need minimum 2 electron volt to just liberate the electron. Just liberate the electron. Then it will come out. Minimum 2 volt is 2 electron volt energy is required. That is known as work function. Okay. So let's say that this electron gains this much energy and it comes out. So this electron is coming out directly. It absorbs energy, immediately it comes out. Okay. Now, electron here, this also absorbs energy. But when it comes out, in its path, there are several obstacles. It collides. It collides with one atom here, then atom here, electron here, atom here, then it comes out. Okay. So in this process, it is going to lose energy. It is going to lose energy. Okay. That means different electrons come out with different kinetic energy. And some of the electrons will have maximum kinetic energy. Which electrons? The electrons which are liberated immediately without any collision. The moment they absorb energy, they are liberated. They come out of the surface without any further collision. So their kinetic energy is going to be maximum. Okay. And this, the variation of kinetic energy. Okay. How do we find out? Okay. So for that purpose, what we do is, we apply a negative potential here. We apply a negative potential. Why? So that when the electrons start from here, electrons are starting from here. Okay. And they are going towards the other plate. Okay. Now, if this plate is at positive potential with respect to this plate, then the electrons are going to gain kinetic energy. But if this plate is at lower potential, negative potential with respect to this plate, then they are going to lose energy. By the time they start from here and by the time they come here, they are going to lose energy. How much energy they will lose? Loss or gain in energy. When a charged particle travels through a potential difference, we have studied all this. Okay, that's why I am not explaining too much. I expect that you remember all those things. Okay. So when a charged particle, electron, proton, any charge moves through a potential difference, okay, it is going to lose or gain energy. Okay. So if it is electron and this is at higher potential, it is going to gain energy. It is electron, negative charge, and this is positive potential, this is negative potential. in this case it is going to lose energy. Now, so by the time it reaches here, it is losing energy. Now, if this potential difference is sufficient such that EV naught is equal to the maximum possible kinetic energy of the electron, in that case, even those electrons which have the maximum kinetic energy, even those electrons are also stopped. They are stopped from reaching here. They cannot reach here. And if the electrons cannot reach here, then the circuit is not complete and current becomes zero. Okay. So the potential difference between these two plates, which can stop even the most energetic electrons, is known as stopping potential. Stopping potential. It is indicated by this point here. This point here. Okay. So at a certain negative potential, that means to stop the electrons, this cathode, this collector should be at negative potential with respect to this. Okay, so the potential difference between this and this is collector minus emitter. It should be negative. If it is negative, electrons will lose energy. And if it is sufficiently negative, which is known as stopping potential, okay, in that case, even the most energetic electrons will be stopped from reaching here. Then current becomes zero. Okay, so at this point, current is becoming zero here. Current is becoming zero. Now, so this corresponds to this point here. This point here corresponds to kinetic energy maximum. Maximum kinetic energy. Okay. Now, what was the expected behavior? The expected thing was this. What was expected? If intensity increases, then the electron will absorb more energy. It will come out with more kinetic energy. And then I will need to require more negative potential to stop it. But it did not happen. This was what was expected, but what actually we observed is that if I increase intensity, provided that frequency is constant, okay, I'm writing it here. Frequency is constant. Okay, so I am using two light, same frequency but different intensity. Frequency remains same. I am changing intensity. I am increasing the intensity. Okay, I expected that for this intensity, the higher intensity, the kinetic energy must also be higher and more negative potential should be applied. The stopping potential should become more negative. Okay, to stop those electrons. Okay, so I actually expected this. I expected this kind of behavior, but absolutely different thing was found. What was found is that no matter what is the intensity, if I change the intensity, the current changes. Why the current changes? More number of electrons are emitted, more number of electrons, so more current. So current increases, but this value here, this does not change. That means the maximum kinetic energy in both cases, it remains same. It does not depend on intensity. It does not depend on intensity. Okay. So this was the expected, this is the actual. All these points you have to note down. Theoretical problems will be asked based on everything that we are discussing now. Okay. You keep on understanding everything. Every point is important. Okay. Okay, now fourth one, dependence of kinetic energy on frequency. Okay, so here what we did, we kept frequency constant and we changed intensity. Here what we are doing, here I am changing frequency. Expected. According to wave theory, no dependence is expected. According to wave theory. Okay? Wave theory does not expect any relationship between the maximum kinetic energy here and frequency of the light. There is no such relation according to wave theory, but that was not found. We found this kind of relation. And what it says is that if frequency is below a particular value, okay, for one particular value, if frequency is one particular value, then electrons are ejected with zero kinetic energy. That means they are just liberated. And when we increase frequency, okay, then kinetic energy keeps on increasing. This was the actual observation that was found. But wave theory could not explain it. Okay, understood? And not only this, okay, if I plot this graph, kinetic energy maximum versus frequency, okay, for different metals, the graph turned out to be parallel. These are different metals. They are. This is some, let's say, zinc. This is copper. This is aluminum. Okay. There are different metals, but this graph, kinetic energy versus frequency, it was found to be parallel. This slope, tan theta, this slope is same for all of them. They are parallel. Now this was absolutely surprising for the scientists. They simply could not explain it. Okay? They simply could not explain it. Then who explained it? Einstein. Einstein explained it using the quantum theory of electromagnetic wave. Okay, the quantum behavior, the quantization of energy, the quantization that we discussed in the previous lecture. He explained it successfully, satisfactorily, and for that he was awarded the Nobel Prize. Okay, Nobel Prize was awarded to Einstein for this explanation, this theory, not for the general relativity. Okay, that is generally thought. Okay, he was awarded Nobel Prize for this explanation. Okay, now what he says, let's try to understand his theory and then try to correlate this theory with these observations. Okay, now the first point, quantization, that we already discussed in the last lecture, that energy of EM wave is quantized in energy packets, which are called photons. The same thing that we studied in the last lecture. Each photon, energy of each photon is h nu. This is nu. This thing is how we pronounce it. Okay, this is how we pronounce it. We pronounce it as nu. H nu. Okay. If you don't like this, you can use HF. You can use HF. It makes no difference. Okay. F for frequency. It makes more sense. But this nu is also kind of a common symbol for frequency. Generally, in most of the books, you will find this symbol. That's why I am also using it. Otherwise, you are free to use F for frequency. Okay, it's not a problem. Okay, so this is the first theory, quantization. Okay. Now, second, the most important. Second one. So, electromagnetic wave. Now, to explain photoelectric effect, do not think of electromagnetic wave as a wave. Think of electromagnetic wave as a wave when you want to explain interference and diffraction. If you want to explain photoelectric effect, think of this as particles. This in itself is amazing, astonishing. It appears as if light knows when to behave like a particle and when to behave like a wave. Think about it. Somehow light knows this. Light knows that this is the arrangement for YDAC. Now is the time to act like a wave. And now this is the setup for a photoelectric experiment. Okay, now let me act like a particle. Well, it does not happen that way. Actually, what happens is, whether a given thing, whether it is light or a particle, a given thing, a given entity, it behaves like particle or wave depending on your observation. If you want to observe it like a particle, it behaves like a particle. If you want to observe it like a wave, it behaves like a wave. Well, think about it. Okay, think about it. Anyway, so what happens is, now when you want to explain photoelectric effect, think of electromagnetic wave like a stream of particles. Stream of photons, large number of photons, not in terms of wave. When you think of EM wave as wave, then you cannot explain this. You have to think of light as a stream of particles. Which particles? They are called photons. Okay. Each photon having this energy. Now, so photons are arriving here on the metal surface. They hit the electrons, and if photon hits an electron, then it transfers all of its energy. Whatever is the energy of photon, all of the energy is transferred to a single electron. This is the most important thing. Energy is never transferred in fractions. A photon is not going to give half of its energy. 20%, 30%, no. It will give either 100% or nothing at all. Either 0 or 100. So photon is going to give all of its energy to an electron. All of this energy is given to the electron. Now what the electron will do? Suddenly it got so much energy. Now some of that energy is required to liberate it from the metal, to give it freedom. Freedom has its costs. If you want freedom, you have a price to pay. You cannot get freedom for free. Freedom is the most costly thing in this world. Most costly. Okay. If you happen to care about it. Then freedom has a price. Okay. So electron has got energy. It will pay some price to the metal. How much price? Every metal has its own price. Okay. That is known as work function. So every metal has its own price, work function. So some of the energy, it is using to just come out, just become free. Okay. And the remaining energy, so electron has got some amount of energy, photon has transferred it, all of its energy, it has got some energy. Out of that, some energy is used to just become free, to be liberated. And the remaining energy is in form of kinetic energy. That's what is written. The rest of energy appears as kinetic energy of electrons. And that's it. This is the simple, beautiful and elegant expression which explains everything. Everything. First of all. Second point. There is no time lag. Because all of the energy is transferred at once. Immediate transfer. It is not given in installments. It's lump sum amount given in one go. Electrons get amount immediately. Then they come out. Immediately they will come out. When they have energy, why they will wait? They immediately come out. Okay. So this point is explained. Now, electrons are ejected only if frequency is more than certain value. Okay. This we can explain from here. It is known as threshold frequency. Okay. To liberate an electron, minimum what energy is required? Minimum energy required to liberate it is known as work function. Okay. So if the energy of photon is exactly equal to work function, then the electron will be liberated, but it will be liberated with zero kinetic energy. Zero kinetic energy. That means all of the energy is going to be used just to liberate. Okay. So that frequency, that required frequency, okay, that required frequency corresponding to this much energy, work function, is known as threshold or cutoff. Cutoff frequency. Okay. Now, if you want the electrons to come out, if you want this effect to happen, then frequency, then energy should be more than work function, or at least equal to or more than. Okay. So corresponding to that, the frequency should be more than a certain value. Only then electrons will come out. It has nothing to do with intensity. Okay. If you increase the intensity, understand this. If you increase the intensity, I have a light beam of a given frequency. Frequency is given, wavelength is given. Okay. Now, if I increase the frequency, if I increase the intensity, keeping the frequency constant, keeping the wavelength constant, if I am increasing frequency, that means number of photons are increasing. Number of photons are increasing, but energy of each photon remains same. So when number of photons are increasing, they will liberate more number of electrons. Current will increase. See here, frequency remains constant, current increases. Current increases, but since the frequency of each photon is same, energy of each photon remains the same. Only the number of photons have increased. So this current has increased. But since the energy of each electron remains constant, so this value remains constant. This value remains constant. So corresponding to this stopping potential also remains constant. Okay? So this explains this point. This point is explained. Okay? And now the last one. If you look at the graph of this kinetic energy versus frequency. What is it? It is of type y is equal to mx plus c. Kinetic energy here versus frequency. It's like y to mx plus c. This m is a constant. This m is a constant. So I'm going to clean all this. Okay, so we explained everything using this theory. Okay. So now after this we are going to solve problems. Okay, we are going to explain just this last thing here. Okay. Okay, it's like this. It's like this here. Okay, so kinetic energy maximum is equal to h nu minus phi. Okay. So this is like y is equal to mx plus c. So that's it. What will be this theta? Tan theta. Okay. So this m is equal to h is constant for every metal. That's why for every metal this slope is constant, because it is equal to h. Planck's constant. And it is constant. It does not depend on it's a universal constant. Okay. So this tan theta is going to be equal to h. Okay. Sometimes they ask what is this intercept. Intercept is going to be negative. You see, intercept is going to be negative. Intercept is going to be negative. Okay. So I have this nu here. This is kinetic energy maximum. Okay. I have this graph. Okay. So if I extend it here, okay. Now this value here is going to give me work function. This intercept, it is negative work function. Okay. This is theta, tan theta is going to be equal to h. Constant for every metal. Okay. Now, one other thing that we need to explain. It's like this. How do we explain this? This is known as saturation current. This is known as saturation current. saturation current. Okay. This is Vc minus Ve. Okay. And this I am saying it as V naught. This is known as stopping potential. Stopping potential. And this here is current. Correct. How do we explain this? Okay, let's look at this setup again. This is my setup. Okay. This is variable potential. Now, if this potential, this is collector and this is emitter, electrons are ejected from here. Now, if this is sufficiently negative, then it will stop every electron from reaching this plate. Okay, and then this current will be zero. No electrons are ejected, but they cannot reach here. Circuit is not completed. Why? Why they are not able to reach here? Because this is at negative potential. This is at positive potential. Negative. Okay? This is positive, this is negative. Electrons are repelled from here and they are attracted towards this plate. They will not go there. And if this difference is sufficiently high, okay, sufficiently negative, no electron can reach here. Even the most energetic electrons will also not reach here. Okay? Alright, it is known as stopping potential. Okay, it is equal to E times V naught is equal to kinetic energy maximum. Okay, so this potential difference is able to stop even the most energetic. And what this is equal to? This is equal to this. Okay, alright. Now, if I slowly start making it positive, slowly, then electrons will start to be attracted towards this plate. Slowly the electric field will, the current will grow, it will increase. Now, if it is made sufficiently positive, then at a certain point, it is able to attract every electron. So whatever electrons are ejected from here, all of them are attracted. At that time my current will be maximum. And after that, even if I increase it further, okay, after this, even if I increase it further, so there are no electrons left. Okay, electrons will be attracted, but the number of electrons will not change. And that's why the current becomes maximum, it becomes constant. There is no further change, even if it is more and more positive. Because there are no electrons to be attracted. All of them are already attracted. Okay? So the current cannot increase. Current will increase only if the number of electrons increase per second. Okay? So this is how we can explain this saturation current. And that's it. That's it about photoelectric effect. We are going to solve problems. So we will solve few simple problems and that's it. And then you will practice few more from the problem sheet and then you will become perfect expert in photoelectric effect. Okay? Okay, let's do a few problems. First problem. Okay. Yes. What is effect of frequency wavelength and intensity on kinetic energy maximum, okay, photo current and stopping potential. Okay, general discussion. What will be effect? Okay, if I change any of these, what will be effect? Okay, so let's make this table. Okay, let's say that let's say that okay, I have this kinetic energy maximum current, that means photocurrent. Photocurrent, the current because of photoelectric effect is known as photocurrent, and stopping potential. Stopping potential. Okay. If frequency is increased, wavelength is increased, okay, and this intensity is increased, you just have to find the effect, whether it is going to increase or decrease or remains constant. Okay, if I increase this frequency, I am going to solve it. Okay, you should stop the video now, stop it now, and then try to get this answer on your own. We are going to discuss it now. Frequency is increased, this is increased, this remains constant. For a given metal, every metal surface has its own work function. Generally, it is few volt, electron volt, 1 electron volt, 2 electron volt, and all that. Now, if I increase frequency, this is going to increase. This is going to increase. So, this also will increase. Okay. Kinetic energy maximum, it will increase. Okay. What about current? What is current? Current is dq over dt. Current will change only if number of electrons change, and number of electrons will change only if number of photons change. One photon ejects one electron. Remember this. One photon, if it is able to eject, then it will eject only one electron. One photon ejects one electron. So if the number of photons remain constant, only the frequency changes. That means the energy of each photon changes, but the number of photons remain constant. That means the number of ejected electrons will also be constant. Current will be same. Current will be same. No change. No change. Stopping potential is directly related with kinetic energy maximum. Remember this. Kinetic energy maximum is equal to E times V naught. This V naught is stopping potential. Stopping potential. That is the negative potential required to stop even the most energetic electrons. That is stopping potential. That depends only on kinetic energy. So if this increases, this also increases. Sometimes it becomes confusing. Okay, what is the meaning of increasing? Okay, so if let's say that initially the stopping potential is minus 500. I increased frequency. Okay, then kinetic energy maximum, this will also increase. Okay, so this is stopping potential. Will it become more negative or less negative? Okay, will it become, let's say, minus 7 volt, or it will become minus 3 volt? What do you think? Okay, it will become minus 7. Okay, now more negative potential is required to stop that electron. The kinetic energy has increased. I will need more negative potential to stop it. It will become more negative. Okay, so generally we do not like to get confused in these things. We talk only in terms of magnitude. The magnitude is going to increase. Okay? And anyway, this is positive. So this also, it is written like this. That means I am thinking it in terms of positive only, not negative. Okay. Understand this? Okay. Now, lambda increases. Okay. So kinetic energy maximum. I can write it in terms of lambda. Okay. So Hc over lambda minus 5. Okay. If lambda increases, this is a constant, this is going to decrease. Now here, by the same logic, energy of each photon has decreased but the number of photons remain the same. So current will be same, no change. And here if this decreases, this also decreases. Okay. Now this is the real confusing one. This is the real confusing one. What is intensity? Intensity. Okay. I is equal to E over A and T. Okay. Intensity increases. That means through any surface, I have this surface. This surface is kept in the path of this light beam which is coming and incident here. It is carrying some energy. On this surface, some energy is incident every second. Every second some energy is incident. It has certain cross-section area. Through this cross-section area, per unit area per second, whatever energy is incident, that is known as intensity. So I am observing this surface, per second I am measuring this, how much energy is incident. From that I calculate intensity. Now, if intensity increases, try to understand this. If intensity increases, that means per second now I am getting more energy. Per second I am getting more energy. That increment in energy can be obtained by two methods. Try to understand this very, very clearly. Otherwise, this is going to be the very, very confusing thing. Effect of intensity. Intensity increases. That means every second now I am getting more energy. That's it. Now, energy can be increased either by increasing number of photons. Energy can be increased either by increasing the number of photons. Every second I am getting more photons. Frequency remains same. Energy of each photon remains same, but number of photons have increased per second. Intensity will increase. Okay. It is one way of doing it. One other way of doing it is keep the number of photons same, constant, but increase the energy of each photon. That way also the intensity is going to increase. Okay. And or we can do both. I increase the energy of each photon. How can I increase the energy of each photon? By increasing frequency. By increasing the frequency. So I increase frequency at the same time. I also increase number of photons. That way also intensity will be increased. Now, what will be effect on these parameters? It will depend on how the intensity is increased. Okay. If the intensity is increased by increasing the energy of each photon, okay, then effect is going to be same as this. Number of photons remain the same, but energy of each photon has increased. Frequency has increased. That means whatever the effect I see here, all of the effect I will see here also. Note it down. I am not writing everything, but okay, if you are increasing your intensity by increasing the number of photons, okay, in that case intensity increases. Now I am increasing this intensity by two methods. Okay, I am taking this thing here. Intensity increases. Now there are two methods. Okay. By increasing the intensity, by increasing frequency. In that case, whatever I observe here, I will observe same change here. Okay, no change. Okay. This is how I am increasing intensity. And if I am increasing intensity by increasing number of photons, energy of photons, okay, frequency is constant. Energy of each photon remains constant. That means this remains constant. but number of photons have increased. Okay, so here I will see no change. Now this will increase, and here I will see no change. Okay, so the effect of intensity, you have to be very careful. Okay, got it? Got the point? Okay, let's do a few more problems. Few more. Okay, simple ones, not very difficult. It's a very simple topic. Once you understand it, it becomes very, very simple. Okay. Light drop wavelength 400 nanometer falls on a metal surface. Of work function, let's say 2 electron volt. 2 electron volt, okay? Find first kinetic energy maximum, stopping potential. Second, threshold, wavelength, and frequency. How will you find it? Okay. Now, first of all, you find energy of photon. Okay. Energy of photon. Are you doing it? Okay. Stop the video. Do it yourself. Whatever comes to your mind. Okay, you do it. Energy of photon, Hc over lambda, is equal to 1240 electron volt nanometer over 400 nanometer. Okay. What it becomes? Okay. It becomes 3.1 electron volt. What is this? This is the energy of photon. This is the energy of photon. Okay. All of this will be given to an electron. Electron will use some of this energy to just get liberated. How much? Equal to work function. Okay. And then the remaining energy appears in form of its kinetic energy. Okay. So the first question, kinetic energy maximum is equal to h nu minus phi. Now this is, we already calculated. H nu is 3.1 minus 2, which is 1.1 electron volt. What is the meaning of maximum? This is the maximum possible energy with which an electron can come. There will be many electrons. You see, all of the electrons will have this much energy the moment they are liberated. But by the time they come out, by the time they come to the surface and then come out of the metal, in that time they can lose energy in many collisions. Okay. So if the electron does not lose any energy, in that case it will come out with this energy. If it loses some energy, then this energy is going to be decreased. This is the maximum possible value. Now, what stopping potential is required to stop it? Okay, so this we integrate with kinetic energy maximum is equal to E times V naught, stopping potential. Now this is 1.1 electron volt is equal to E times V naught. E gets cancelled by E. You see, that's how we do it. It's very interesting. E gets cancelled by E, okay, then V naught is equal to 1.1 volt. This is my stopping potential. Okay, that's how we calculate. Think about it. Okay, that's how we calculate. So simply, we don't have to bother too much. We don't need to convert this into joule and doing all the calculation. Okay, even if you do that, you are going to get the same answer. Okay, you have to learn this method. very interesting. Okay, threshold wavelength and frequency. Threshold wavelength. What is the meaning of threshold? Threshold wavelength, threshold frequency. What is the minimum energy that is required to liberate it? It is equal to work function. Now, what is frequency corresponding to work function? What is work function? Minimum energy required to just liberate it. Okay, so what should be the corresponding frequency? That is known as threshold frequency. Okay, so and what is the corresponding wavelength? That is threshold wavelength. Okay, so Hc over lambda is equal to 5. Okay, now Hc is 1240, or it's like this: lambda is Hc over 5. Hc is 1240 electron volt nanometer divided by phi is 2 electron volt. So this gets cancelled. I have 620 nanometer. Now let's try to understand this. What is this? This is threshold. When the wavelength is exactly this, then electron is going to be liberated. Just liberated. If I want my electron to come out with some kinetic energy, then wavelength should be more than this or less than this. Think about it very, very carefully. It should be less than this, because when I increase wavelength, energy is going to decrease. I want the electron to come out. That means the energy of photon should be minimum this. It should be more than this. Then wavelength should be less than this. Okay, that means this is known as threshold wavelength. Okay, so lambda should actually be less than or equal to lambda. Only then electrons will come out. Okay, so if the wavelength is, let's say, 700 nanometer, electrons will not come out. Okay, if the wavelength is 500 nanometer, electrons will come out. Okay, now once I know wavelength, I can find frequency. Okay, you see. Okay, and this it's like this: speed. Okay, so h nu is hc over lambda. So nu naught is c over lambda naught. Okay, so 3 into 10 power 8 over 620. Okay, so 6.2 and 10 minus 7. Okay, in meter. This is approximately equal to 5 into 10 power 15 hertz. 0.5. 0.5 into 10 power 15. So 5 into 10 power 14 hertz. This will be the threshold. This is the threshold frequency. If the frequency is exactly this, electron will just be liberated. It will come out with zero kinetic energy. I want the electron to come out with some kinetic energy. Energy should be more than this work function. That means this frequency should be more than this. Okay, so this frequency should be more than or equal to threshold. Only then electrons come out. Okay. All right. Let's do few more problems. Okay. Let's complete it in this lecture itself. Okay, we are going to complete this chapter. Okay. Light of wavelength. Okay, light of wavelength 500 nanometer falls on a metal plate. Okay. A potential difference of 1.48 volt is required to completely stop completely stop the current. Okay, that means photocurrent. Find first kinetic energy maximum and work function. And second, kinetic energy maximum and stopping potential if wavelength is changed to first 1000 nanometer and second 2000 nanometer. Okay, threshold wavelength. Okay, do this problem. Okay, then in the meantime I'm thinking of one other. Okay. Okay. When wavelength of light falling on a metal surface is half, then stopping potential or stopping voltage, stopping potential, okay, it means the same, you don't have to be confused. Stopping potential changes from 1.8 electron volt to 5.8 electron volt. Okay. What was original wavelength? Okay. Light of intensity 50 watt per meter square. Okay. Wavelength 620 nanometer. Okay, falls on 20 centimeter square surface of metal. Okay, light of intensity 50 watt per meter square, wavelength is given, 620 nanometer falls on metal surface. Okay, some metal surface area is given. Okay, what is find maximum current. Maximum is saturation. Okay, saturation current if, okay, find maximum current assuming 80% efficiency and work function 1.5 electron volt. Okay. I hope that you are able to see this clearly. Are you able to read all of this? Okay, I will read it for you. Okay, I am going to read it for you and let's do it quickly. Okay, let's complete this in this lecture itself. First question: light of wavelength 500 nanometer falls on a metal plate. A potential difference of this is required to completely stop to completely stop the current. That means it is stopping potential. This is the stopping potential. The stopping potential equal to what? 1.48 volt. It is already given. Wavelength is given. You can find energy of photon. I have to find kinetic energy maximum, work function, and threshold wavelength. Threshold wavelength. Okay. Then what will happen if I change the wavelength? Okay. Are you able to read all of this? Let me read it out for you. And then you will stop the video, pause the video, do it yourself, get some answer. And then we are going to discuss it. And then this will conclude. Okay. Second question. When wavelength of light falling on a metal surface is halved, it is made half, then stopping potential changes from 1.8 electron volt to 5.8 electron volt. What was the original wavelength? Okay, so when I half the wavelength is made half, stopping potential changes from 1.8 to 5.8. So what was the original wavelength? Interesting, okay, I can find original wavelength. Now, next one. Light of intensity 50 watt per meter square, wavelength is given, falls on 20 centimeter square surface of metal. Okay, a metal surface, intensity is given, wavelength is given. Now, find saturation. What is the meaning of saturation current? When all of the electrons are attracted. So whatever electrons are ejected, all of them are attracted by the collector. Then the current is maximum. Okay. So I have to find that maximum current. That means all of the electrons are able to complete the circuit and be part of current. Okay. Assuming work function is given 1.5 electron volt and 80% efficiency. What is the meaning of 80% efficiency? What it means is, if 100 photons are incident, they should emit 100 electrons. Okay? But 100 electrons are not emitted, only 80 electrons are emitted. So 100 photons, energy of 100 photons is absorbed, but somehow 20 electrons are not able to come out due to whatever reason. Only 80% electrons are coming out. So we are assuming 80% efficiency. Assuming this, I have to find the maximum current, saturation current. Okay, I explained all of that. You should pause the video now and do all the problems. And now we are going to discuss it. Okay, first thing, energy of photon. H nu is hc over lambda is 1240 electron volt nanometer over 500 nanometer. 500 nanometer. Okay. This becomes 5 and this 2.48 electron volt. Okay. This is stopping potential. We just discussed it. Okay. So it's like this. First, kinetic energy maximum. Okay. Is equal to. Okay. It is equal to h nu minus phi. Okay. Now, kinetic energy maximum is equal to E times of V naught. Okay, let me write it like this. Okay, E times V naught. This is equal to V naught is given 1.48. So this becomes 1.48 electron volt. Kinetic energy maximum. So whatever is the stopping potential, maximum kinetic energy is that much electron volt. It's a very good way of remembering it. The stopping potential is 5 volt, maximum kinetic energy will be 5 electron volt. Maximum kinetic energy is 10 electron volt, stopping potential will be 10 volt. Okay? We do not calculate it, I do not convert this into joule and doing all those lengthy calculations. You have to understand this direct relation. Kinetic energy is 10 volt. Kinetic energy is 10 electron volt. I need to apply a potential difference of 10 volt. to stop that electron. Okay, stopping potential is 1.8 electron, 1.8 volt. So maximum kinetic energy will be 1. Same in electron volt. Now, kinetic energy maximum is equal to h nu minus, this is work function. Okay, so phi is equal to h nu minus kinetic energy maximum. This is 2.48 minus 1.48. It is 1 electron volt. 1 electron volt. Okay. Now what will be threshold wavelength? Threshold, okay. Hc over lambda naught is equal to phi. So lambda naught is hc over phi. Hc is 1240 electron volt nanometer over phi will be equal to 1 electron volt. 1240 nanometer. What is this? What is this? This is threshold wavelength. That means if the wavelength of light is exactly this, in that case the energy of photon will be 1 volt, 1 electron volt. Okay. Work function is also 1 electron volt. Okay. So when the electron is ejected, it is ejected with zero kinetic energy. Now, what will happen if wavelength is more than this? If wavelength is more than this, in that case, energy of photon will be smaller than 1 electron volt. It will be smaller than the work function. Electron will not be ejected. Okay, that means in this case, electron is not going to be ejected. If you look at the energy here, energy of this energy of this photon here, okay, it will be 1240 over 2000. Okay, this will be equal to 0.62 electron volt. Okay, energy of photon having this wavelength will be 0.62 electron volt. The minimum energy required is 1 electron volt. That means this light cannot eject electron, no matter what is the intensity. Okay, you understand this? Now what about this here? Okay, 1000 nanometer. 1000 nanometer. What is going to be energy? H nu is going to be hc over lambda. 1240 over 1000. 1.24 electron volt. This is energy. Okay. So what will be kinetic energy maximum? Kinetic energy maximum in this case is 1.24. This is the energy of electron. All of this energy will be given to the electron. Out of that, 1 electron volt will be used to just liberate it. Okay. Rest will be kinetic energy minus 1, 0.24 electron volt. So what will be stopping potential? Stopping potential. It is simply 0.244 volt. Direct relation between energy and potential. Okay, try to understand this very well. Stopping potential 1.48 volt. Kinetic energy maximum 1.48. Same in electron volt. Kinetic energy 0.24 electron volt. Stopping potential same value in volt. Okay, are you able to make this connection? Remember this. Okay. Now, next one. Okay, next one is like this. When wavelength of light falling on metal surface is halved, then stopping potential changes from 1.8 to 5.8. Stopping potential has increased. Why? Because the kinetic energy has increased. Why kinetic energy has increased? It is because the energy has increased. Energy of photon. Why energy of photon has increased? It is because wavelength has decreased. Okay. So Hc. Okay. First place. kinetic energy maximum is hc over lambda minus phi. Okay. First case, this is EV naught. EV naught. Stopping potential is 1.8 electron volt. Oh no. Stopping potential changes from 1.8 volt to 5.8 volt. It's my mistake. Okay, so this is stopping potential. What will be kinetic energy maximum? The same value in electron volt. Okay, so it's like this: 1.8 electron volt is equal to hc over lambda minus phi. Okay, now second, it becomes 5.8 electron volt. This becomes half. This becomes half. So 2 times of hc over lambda minus phi. Okay, you got it? Now, minus this. When you minus it, it becomes 4 electron volt is equal to hc over lambda. That's it. This gets cancelled. Okay, so lambda is equal to hc over 4 electron volt. That's how we calculate. You have to learn this method of calculation. Otherwise, you will you will have to do it in a very lengthy calculation. Electron volt, change it into joule, and then make all sort of put this value of h and c and all this. Okay. All of these questions can be solved within minutes. Within 1 minute, you should be able to solve it. Okay. If you are taking more time, if you are taking more than 1 minute, even 1 minute is maximum. Even 1 minute is maximum to solve such problems. Within seconds, 10-20 seconds, you should be able to solve it and get correct answer. If you are taking more time, you have to understand this connection, how we are making this calculation. Okay, hc is 1240 electron volt nanometer over 4 electron volt. What do I get? 310 nanometer. That's it. This was the original wavelength. Okay, that's how we do it. Okay, now the last one. Okay, let's conclude this. That's the last problem. Then many more problems in the problem sheet. You must do it. You must do it, okay? Now, light of intensity this, 50, wavelength this, falls on whatever is given. Find maximum current assuming 80% efficiency and work function. Okay. First of all, let's calculate energy. H nu is equal to hc over lambda 1240 over 620. This becomes 2 electron volt. Okay, phi is equal to 1.5 electron. Okay, that means electrons are emitted. Okay, kinetic energy maximum is 2 minus 1.5. This is 0.5. Now, electrons will be emitted. There will be current. Now, what it is? Current will be equal to current I is equal to dq over dt. Okay, that is charge flowing per second. Okay, in 1 second, how much charge flows? To find that, I will have to calculate in 1 second how many electrons flow. If I know how many electrons flow in 1 second, then I can find how much charge flows in 1 second. And then I can find current. Now, how many electrons will come out? It will depend on the number of photons hitting per second. Okay, now what is intensity? Intensity is equal to energy over area into time. Okay, so E over T is equal to I into A. It is equal to 50 into area is 20 into 10 power minus 4. What it becomes? 1 and 2. So 1000 0.1. This is 0.1 joule per second. What is this? This is energy received by the surface per second. In 1 second, surface is receiving 0.1 joule per second. Okay. What is energy of one photon? Energy of one photon is equal to 2 electron volt. 2 electron volt. Okay. Now number of photons. Okay, incident falling per second. Let's say n is equal to, this is total energy. All of that energy is in form of photons, each photon having this energy. Okay, so how many number of photons? 0.1 divided by 2 and 1.6 into 10 power minus 19. Okay, so it's 1 over 32. It's 1 over 32 and 10 power 19. What is this? These many photons are falling on the surface per second. Okay. And how many electrons are ejected? 80%. Number of electrons ejected per second. You see, per second. Okay. Per second is equal to n into 80 over 100. 80 over 100. Okay. This is equal to 10 power 19 over 32 into 80 over 100. Okay. So this becomes 4. It becomes 0.25 into 10 power 18. 0.25 into 10 power 18 watt. Electrons per second. Okay. You see, there is no role of this value. Why there is no role? It is just to, this is just to check whether the electrons will be emitted or not. Once the electrons are emitted, no matter what is the kinetic energy, they are going to be part of the current. Okay, understand this. So 80% efficiency. So what is current or what is charge flowing per second? Okay. What is charge flowing per second? Okay. So current is equal to charge flowing per second. Okay. You see, this is number of electrons flowing per second. 0.25 into 10 power 18. 10 power 18. Okay. This is number of electrons flowing per second into charge of 1 electron. Okay, it is 1.6 and 10 power minus 19. This is going to be equal to 0.4 and 10 power minus 1. Okay. This is 0.04 MPa. Okay. That's how we do it. Okay. And that's it. Let's conclude. This was photoelectric effect. All concluded, but it's not complete until you do the problems from the problem sheet. Okay? It will remain half complete unless you also do your part. That is most important thing.